right, welcome back. This is part 3 of the mini-series, Chemical Kinetics, expressing a reaction rate. And we will be working on the last example problem before we move on. So this is a textbook problem from the Pearson's Principles of Chemistry, a Molecular Approach textbook. It can be found at the end of chapter 13. It's question 8. And the question is considering the following reaction. Nitrogen dioxide is transforming into nitrogen monoxide and oxygen gas, and we're told that the following data was collected for the concentration of nitrogen dioxide as a function of time. And this is kind of cool to see. This example problem is showing us kind of what we've been talking about, this idea that the reactant concentration decreases as time goes on. Looking at this chart, we see that time is increasing as we go down the column, and similarly, the concentration of our reactant, nitrogen dioxide, is decreasing as that time is increasing. So that's kind of a cool visual just to put kind of a picture to what we've been talking about. So for part A, the question is, what is the average rate of the reaction between 10 and 20 seconds, and then between 50 and 60 seconds? And first thing I would do, like we did in the previous problem, is I would just start by kind of writing out the reaction rate. And having that generic definition that we've been writing. I'm going to write it in a different color. And we'll be able to use this for both parts. So I'm going to say my rate of the reaction is equal to, and we'll work on this reactant first. All of these, except for oxygen gas, has a coefficient of 1 in front of it. It's an invisible 1. So we'll have negative change in nitrogen dioxide over a change in time. Normally we would put the coefficient 1 over 1 divided by that coefficient. However, since our coefficient is 1, we don't really have to write 1 divided by 1. So I'm just going to leave it like that. We'll have that equal to our products. Our first product is nitrogen monoxide. That also has a coefficient of 1 in front of it, so I'm just going to write positive that. And then that's going to be equal. 1 divided by 1/2 is 2, so we'll have positive 2 times the change in concentration of the oxygen gas over change in time. And that's our just rate reaction for this whole equation that we were given. And now we can go ahead and get started. Alright, so what we're going to we'll look at the 10 and 20 seconds first. Go ahead and just star those so we know where we're looking. The way I like to write this is I'll put in brackets the concentration of nitrogen dioxide at time is 10 seconds is equal to 0.951 molarity. And then we also know that the concentration of nitrogen dioxide at time equals 20 seconds is equal to 0.904 molarity. And now all we're looking is the average rate of the reaction. So I can, right now, just looking at those first two terms. So I can say my rate is equal to negative. And recall that delta just means final minus initial. If I know that I'm starting initially at 10 seconds in this case and going to 20 seconds, my initial state is 10 and my final state is 20. And I can just subtract those. I'm going to do that in parentheses for the concentration. And then we'll divide that by the change in time. Now, if I go ahead and simplify the numerator, that comes out to be negative 0.047 molarity divided by 10 seconds. And then if I go ahead and do that division, my negative signs will cancel out, and I'm left with positive 0.0047 molarity per second. And that would be my first rate. So the rate of the reaction would be equivalent to this right here. That would be the average rate between 10 and 20 seconds. For the second part of part A, we can kind of approach it the same way. At time equals 50 seconds, I'm going to go ahead and erase this over here. This would be our new initial state. The concentration of nitrogen dioxide is 0.778 molarity, and the concentration of nitrogen dioxide at 60 seconds is 0.740 molarity. Once again, we'll just use that rate equation that I have in brackets, kind of took out. It's going to be equal to negative, and then in parentheses I'll do my change in concentration first. Divided by the change in time. If I go ahead and simplify that numerator, it comes out to be negative 0.038 divided by 10 seconds. And if I simplify that again, negative signs cancel out, and we get 0.0038 molarity per second. This is interesting to see. We can see that not only is the concentration of nitrogen dioxide decreasing, but the rate, this overall rate is also decreasing. It was at 0.0047. It was faster at the beginning than it was. It's slowing down. So that is how we would solve part A. I'm going to go ahead and erase everything in blue, and then we'll work on part B. Alright, so now everything is sort of erased. We just have that rate equation. Part B, I did change it just a little bit from what the textbook had. It was asking for the rate of formation of the oxygen gas between 50 and 60 seconds. But I thought I would just make it a bit more challenging and show you that we can actually solve this for a different time. It doesn't have to be the same. So since we have, we're asked for the rate of formation of oxygen gas, we don't really have any information in this table about how fast the oxygen gas is being produced. But we know how fast, and we can figure out the average rate of how fast nitrogen dioxide is being consumed. We can figure that out for the time 60 to 70 seconds, and then we can actually convert that to oxygen. And we have the pieces that we need. We have this in our equation, and since everything is equal to each other, the rate of consumption of nitrogen dioxide has to be equal to the average rate of production of the oxygen gas. So we can make a new equation that will look like this. And we would be solving for this piece. This is what we want. And we can figure out, similarly like what we just did in part A, where we were looking for the average rate of the reaction between two periods of time, we can do that for the nitrogen dioxide. We have those pieces of information, and then we can just do the math to solve for the rate of formation of the oxygen gas. So we'll do it like we did just before. I'm going to write over here my concentration of the nitrogen dioxide at 60 seconds equals 0.740 molarity, and the concentration of nitrogen dioxide at 70 seconds is equal to 0.704 molarity. And then I can go ahead and I'm going to just figure out what the left side of my equation is going to be, and then we'll solve the problem. So we have that negative sign, and then we'll have 0.704 molarity minus 0.740 molarity divided by the change in time, which is between 70 seconds and 60 seconds. That's going to equal 2 times the change in concentration of oxygen divided by the change in time. I'm going to focus on the left side first and simplify that before we concern ourselves with the right side of the equation. So if I do the math in that numerator, we're going to get negative times negative 0.036 molarity divided by 10 seconds. This will come out to be positive 0.0036 molarity per second. And I'm just going to do 2 steps in one. I'm going to simplify this left side of the equation, and I'm going to isolate this part of the equation, the rate of the oxygen gas. I'm going to do that by multiplying by the reciprocal of 2 to get rid of that 2 on the right side. I'm going to do that on this side too. So really I'm doing 1/2 times 0.0036 molarity per second. Alright, and then if we go ahead and just do the math over here, we can see that the rate of formation of oxygen gas between 60 and 70 seconds is equal to 0.0018 molarity per second. And that's how fast, that is the rate at which it is forming at that period of time. We don't have to do anything else. It's asking for a rate. If it was asking for a concentration of the oxygen gas, then we would do an additional step where we plug in the change in time in the denominator and solve for the concentration. But because it was asking for a rate, we want our answer to be in units of a rate, which is molarity per second. So that was kind of a shorter video. If you have any questions, again, just drop them in the comments. I'd be happy to answer. And I'll see you next time.